Started. So, welcome to today's lecture on debugging parallel programs. First, as always, I want to provide a short overview of what we're going to talk about. We're going to discuss two issues with debugging today. First of all, functional debugging, where it's really about bugs in your program, incorrect output, your program crashing, and so on. And then we're going to talk about performance debugging, where it's really about how much execution time do you spend, where do you spend it, how do you find that out, and so on. And for each of those two categories, we're first going to talk about a few generic guidelines, which are extremely important in parallel programming. I cannot stress that enough, but I will try to do so throughout this lecture. And after these generic guidelines, we'll get into what to do about serial programs, because a lot of that still applies to a parallel context. And then we're going to talk about parallelism specific debugging. And as you know, I like to always present the motivation for the topics that we talk about in a lecture. Need to enable desktop audio for that one. And what you will see is just a minute or so of a video that shows the launch of the first Ariane 5 rocket back in 1996.
A final decision to go was taken.
So everything is fine so far. We're 10 seconds away from start and probably 15 seconds away from liftoff or so. At some point the center stage will start, which seems to be working nicely. A few seconds after that, the boosters on the side will also start and the rocket will lift off. So now they're producing around, I don't know, somewhere between 10 and 15,000 kilonewtons of thrust. Everything is going really nicely. This was the newest and best rocket the ESA came up with in the 90s after years and decades of research. And at some point, very soon, gaining height so far, everything is fine, still. It just breaks up. So what happened, I don't know if you saw, I can probably stop the video somewhere around here. The thrusters of the rocket started to point into a different direction in order to turn the rocket. Which obviously shouldn't have happened here because it was pointing almost straight up. It was exactly on its flight path. So why did the control system deviate from the actual flight path that it was intended? So this is quite a funny story. They use sensors to get information about the direction where the rocket is pointing. I'm not going to go into the exact trigonometry and math and physics and so on, because I don't know it myself either. It's just the point of the angle where the rocket is pointing in the sky. They get measurements, and those measurements are 64-bit floating point numbers. For the control system, the flight control that is actually controlling the direction where the thrusters are pointed at, or pointed in rather, these use integer numbers, 16-bit integer numbers. So what they have to do, obviously, is they have to do a number conversion from 64-bit floating point to 16-bit integer. So far, no problem. Of course, a 64-bit number can store, or 64-bit data value can store much larger numbers and a much larger number range than a 16-bit value, so you might have overflow issues at some point. They did have, and that's actually what happened here. So basically, the system reported larger numbers that it could not represent in a 16-bit integer. They had an overflow. The rocket thought it was pointing 90 degrees sideways or something like that. The thrusters attempted to correct this mistaken idea that the rocket is pointing sideways. So the rocket started to actually point sideways, and it just broke up. Now you might think, okay, this is a project where they probably spent billions of research. How could something like this happen? And this is due to using legacy software, basically. So they used the control systems of the Ariane 4 rocket, the predecessor. And back then, they didn't have the computational power to do exception checking for all the number conversions they were doing. They could only do a handful of variables at the same time. And this specific variable, for this specific variable, the check was disabled because the flight profile and the physical properties of the Ariane 4 rocket prevented this value from ever exceeding the 16-bit range. So they thought they would never have to check this value for sanity anyway, because no matter what you did with this rocket, if it actually exceeded this value range, it was already breaking up anyway. Afterwards, they just basically copy-pasted the source code to the Ariane 5 code base, reused the same environment and everything, but the Ariane 5 is a much more powerful rocket, so it can actually exceed this flight profile, and it would have needed this exception handling, which would have been perfectly capable of solving this issue in flight, so nothing would have happened. The check was still disabled, however, and the first launch basically was a failure. I mean, it's always relative talking about failures with stuff like that, because you still get a lot of information simply when you launch a rocket and it only flies for 30 seconds. It costs billions of dollars or euros, whatever, but you still get a lot of information about spaceflight and so on. So failure in this regard is always a relative term, but yeah. So why do we need debugging? Well, it's simple because we make mistakes. I think there was a study, I heard this one in one quality engineering lecture 15 years ago, that there are studies that show a good programmer makes a programming mistake on average every 30 to 50 lines of code or something. I don't know. But just nobody's perfect, not even the best programmers. We still need tools to help us with that. And why do we need a lecture about this? Well, first of all, I would like to tell you about some tools that are out there that I've been personally using in the past. And second of all, because it's complicated enough to have a lecture about this. I could now argue why it's very complicated, but it's much simpler to just paste the question and answer, actually the first entry of the FAQ of the OpenMPI FAQ. That's specifically debugging applications in parallel. That's the section, and the actual question, the very first question is, how do I debug OpenMPI processes in parallel? And the answer to that is, I kid you not, I copied this from the website, probably could have linked the website here. This is a difficult question, then some follow-up text, and afterwards this FAQ section does not provide any definite solutions to debugging in parallel, and some text afterwards. So since these are the OpenMPI developers and maintainers and designers, part of these people also designed the MPI standard, this should show you what a difficult topic this is, and I have to disappoint some of you. I'm not gonna talk about some auto-magically well-suited tool that you can simply throw your parallel program at, and it's gonna immediately tell you, you have a race condition in line 32 or something, or you have a deadlock in your MPI communication pattern, or you're reusing a buffer before the send operation completed and stuff like that. Without additional effort, you're not gonna get any of this kind of information. This simply doesn't work because the topic is much too complicated. At some point, maybe we will arrive at an AI system that can tell us what we did wrong, but probably if we ever arrive at that point, we have an AI that can write these codes for us. So I don't know. Let's see how that goes. In any case, let's dive into the topic itself, but I would like you to reduce your expectations a bit, probably, because this is extremely difficult and a lot of effort still relies with you, the programmer. So, let's first talk about functional debugging. Functional debugging basically means everything that results in you not getting the correct program output. This could be either, for example, because the program crashes. It could be because the program is not finishing, which means you have freezes of your program, deadlocks, you have infinite loops even, where you're not locked in some state, but you simply do not make any additional progress. Or it could be incorrect output. And these are actually sort of ordered according to severity. Because I really, really love program crashes. Why do I love program crashes? Because they are extremely easy to debug. I immediately see that something is wrong. So I can just throw my debugger at it. I can use Valgrind or something. I can use GDB, and I can check, why is this crashing? Is it a seg fault because I'm trying to dereference a pointer that is not initialized? Where should this pointer have been initialized, and why was this code not executed, and so on. Program crashes are really easy to debug in the grand scheme of things. The second one is your program not finishing, which is also sort of good because you still have the impression that something is not working. If you, for example, expect your program to generate output every 3 seconds, and after 10 seconds you do not see any output anymore, you probably start to get suspicious that something might be hanging there, right? It's still more difficult because crashes are usually immediate, and for programs not finishing, it's sort of the halting problem, right? If you have a program that outputs data every 5 or 10 minutes, how long are you gonna wait until you decide this is no longer working? So yeah. And the worst of them all is incorrect output. Because incorrect output, and I think I mentioned it once or twice, is quite difficult to debug because the first two, crashes and programs running indefinitely, I can try to debug myself even I have no idea what the program is doing. Let's take an astrophysics code, let's take a code from biology, genetics for example. I do not need to know what the program is doing in order to realize if it crashes, something went wrong obviously, and I can try to figure it out from my computer science perspective. Incorrect output doesn't really work in debugging unless you know the semantics of the program. I need to have the domain scientist next to me to tell me, okay, this value was computed as being 5, but I know for a fact it should be 9, so something must be wrong. And then you need to start to trace back and see where is the first time something is not the value that you would expect it to be. So those are quite difficult, and unless you know beforehand or you have a rough idea around the value range or the exact value that you expect for output, you don't even know that something went wrong. But I think we discussed this already. The next thing that you should be aware of is that errors can be deterministic or non-deterministic. We discussed this already a little bit with our Monte Carlo computation of or approximation of pi. And important here to note is simply that you should ensure a reproducibility or try to maximize it as much as possible during testing. For example, fixing random seeds, fixing scheduling policies, fixing affinities and so on, fixing even the number of threads, for example. Also varying those is important, which will be on another slide, but in order to do the actual debugging to figure out what's going on, try to fix as much as possible in your environment to really nail it down, because it could be that your algorithm works with 5 threads, but it doesn't work with 6 threads. Would be a really strange programming bug, could be undefined behavior because you forgot to initialize something, but this can happen. And the thing here is really everything that applies to debugging serial programs is crucial in a parallel context. Because think of everything that could go wrong with a sequential program. You have values not initialized, you have wrong computations happening, you might have overflows of data values, of data ranges and so on. And all of the things that can happen, add to that the fact that you have multiple of these entities that communicate with each other and change each other's state that way, in a non-predictable or non-deterministic way, because if you have a race condition, for example, this depends on scheduling and performance, and this is not deterministic, as we discussed in the past. And if you know for a fact, for example, if you're writing an OpenMP program, we discussed this, you can simply remove all the pragmas by simply removing the compiler flag, and if the program doesn't run correctly in a sequential fashion, don't try to fix it in the parallel context, fix your sequential implementation first, obviously. Now, there are a few coding guidelines, and this might seem now a little bit like I'm giving a quality engineering lecture on how to write proper code, which partially I'm doing here actually. I never was affiliated with quality engineering with the research group, but this is actually information that I'm not just trying to put on a slide because it sounds nice and we are trying to play a keyword bingo here or something like that, but rather that this is actually experience that we've gained in the projects that we worked on. I personally worked on the all-scale project, and before that on Insieme, which was a source-to-source compiler for C++. So we wrote a compiler that is able to translate C++ code into an intermediate representation. We didn't parse, I'm just going to tell you, we didn't parse C++ ourselves. We used Clang for that, but out of Clang we got the CAST, and the CAST then we ourselves translated to our own intermediate representation, and we have a full synthesizer that is able to generate C++ code out of this intermediate representation again. It was a huge project, ran for, I don't know, 10 years, a total of probably 25 to 30 people worked on it in total, not at the same time. And at some point, or at a few points in time, it got really, really complicated. And this is all knowledge and experience we gained, and this is quite something that I would like you to adhere to and to ingest basically, because it's really useful. So first of all, you should try to write clean code as much as possible in order to prevent bugs before they even happen. The best bugs are those that never occur because you wrote code in such a way that they cannot occur. So first of all, and some of them are familiar because we already talked about it, use meaningful identifiers. Don't use overly short variable names because you're too lazy to hit the keys on your keyboard, right? That's really no reason. You have a variable that is an iterator, and it's a little bit more complicated than just an integer in a for loop or something, then simply call it iterator, for example, or call it it, which is a frequently used pattern in C++. Don't give them short identifier names like P or Q or S or something if it's not immediately clear what that means. Also, and we specifically had this example yesterday, try to minimize the vertical distance of variables. Declare the variables just before they are used unless you have a very good reason not to do that and to declare them earlier than that. Because that reduces the amount of code you need to look at when debugging, and it's much easier to just have the entire code that's relevant fit on a single screen, for example, with a reasonable font size and everything, compared to having to scroll around or use your IDE that hopefully helps you and tells you, okay, this variable is an integer, and maybe it even tells you when it was declared and so on. And by the way, this also relates to the identifiers. I would like to not see codes, I mean not for the proseminar, but in general, where you put the type of the variable in the identifier name. Very often for old codes, you see something that says argument, and then it's argument string or argument int or something, because the programmer wanted to convey in the name what the type of the variable is. So when you only use the variable and you're much very below the declaration of the variable, you see immediately what the type is. This is useful if you're working with a plain, stupid text editor that cannot tell you this information. But this is not what you should use for programming. For programming, you should use a developer environment like Visual Studio, Visual Code, Eclipse, CodeBlocks, whatever you use, Vim. And ideally, those tools can tell you the type of a variable just when you click on them or when you hover over them with your mouse. So there's no reason to garbage up the variable name by putting the type in there. Please try not to do that. If you do that, probably you should change your source code editor. Also, with regard to minimizing the vertical distance, try not to use OpenMP private unless you really need it. Because it's much easier, at least in my opinion, to simply omit the private clause and declare variables inside the parallel region. Much more readable code removes the private clause, reduces the vertical distance, and so on. And there's no overhead from declaring a variable inside the loop, because if there's some optimization which makes your code faster by moving the variable outside the loop, the compiler is probably going to do it anyway for you, right? So depends on how it's declared and so on. In general, you should try to follow the dry principle, so the do not repeat yourself principle, which means only have a single component per feature. I very often see this both at the university and in the outside world, that people like to copy code because they think, okay, at this code location, I need something that I already implemented 3 days ago, so let's just copy paste the code there. 3 days afterwards, you need to change it, and then you need to change it in 2 positions, and if it's not 3 days but 3 months after that, you're gonna forget about one of the 2 locations. And then you have 2 source code sort of listings that should do the exact same thing. One of them was updated, the other was not, and then at some point people are gonna be surprised about the bugs they find. In general, try to stick to the rule. If you copy a single source code line that's not too long, probably it's okay. If you already start to copy 2 lines of code, you should be thinking, well, maybe it makes sense to actually outline this into its own function, because I seem to be needing those 2 lines in at least 2 locations. If those 2 lines always appear next to each other, as neighbors, so to speak, let's just outline them into a single function. And if it's 3 or 4 or more lines than that, then probably something like that should obviously happen. And many people think they need to refrain from doing that because if you outline, then you have function calling overhead at runtime. But please, again, think about the compiler, and the compiler can do optimizations like that for you. If the function is very small, it's used in a few places, it's probably not going to increase the instruction size of your binary for too much, then the compiler will inline this function again anyway. And outlining the function helps you as the programmer in order to have readable and maintainable code. It's probably gonna take a few nanoseconds longer to compile the code then, but the resulting binary might actually be the same. So don't over-optimize again unless you know that this is really an issue. And if you have an issue with inlining in the compiler, maybe you should start to look into compiler flags or even changing your compiler, because those functions are quite mature these days. I could go on with code requirements or coding guidelines, how to write clean code, but I actually have a book recommendation on the next slide. I'd rather like to switch to toolchain things that you should use. First of all, you should, as Yoda tells us here, you should read and heed compiler warnings. Try to compile with WR enabled, with W extra enabled, with pedantic if you can afford it, and really try to pay attention to every compiler warning, because most of the time there's a very good reason the compiler tells you that something might be used in an uninitialized context or something. This is very bad, ignoring those. I remember I had a student colleague from 10 or 15 years ago that asked me whether there was a flag to not enable all warnings, but disable all warnings. And basically, yeah, I almost dropped off my chair at that point. Don't do that. Use all the help that you get from compilers, because most of the time there's a very good reason. And in those very, very few instances where you know the compiler will emit a warning and it's a false positive, try to disable the warning only for this code portion. There are pragmas for that. There are attributes for that. You can disable and enable warnings for specific lines of code. Don't disable warnings for your entire code base. That could be 100,000 lines of code if it only applies to a single line or to a few locations, for example. Then disable it for this compiler only, for this line or these locations only, and keep the warning active for the remaining code project. First of all, because you don't run into the issue where others make mistakes and they don't realize it because you disabled the warning. And second of all, you should still disable the warning for your location, because it's quite nice to just see this compiles without any warnings whatsoever. If at some point a commit introduces just a single warning, this is immediately visible. If you already had 10 warnings in there and now it's 11 warnings, you might not catch on. So try to keep the code base as clean as possible. You should also write unit tests and have them regularly run, both unit tests and integration tests. You should have them run automatically using continuous integration tools. There are many out there, for example. If you have projects on GitHub, you can run them with Travis CI or something. Those services are free, most of them at least. If you need higher performance, you probably need your own CI system in your company, for example, at home, whatever you do, that runs these tests. But really use all the automated tools that are out there. If you deal with parallel programs, then use unit tests or integration tests that, for example, vary the degree of parallelism. So you have a set of input, you know the expected output, and then just run your algorithm with everything from 1 thread to 16 threads, for example. Even with over-provisioning, for example, because the continuous integration thing is going to run on some hardware system for which you don't care about performance or oversubscription or slow execution times anyway. You only care about functional debugging at this stage. So try to really vary and play with everything that's possible in order to figure out whether there might be an issue. Also use code coverage tests. For those of you who don't know, code coverage tests are tools that check which source code lines are actually used when you execute a program with a certain input, and which source code lines are, for example, unreachable, either because even looking statically at the code, they will never be executed, or with a certain set of input data, they will never be visited because, for example, in your input data, you could select the numerical solver that you use. You have 3 available, and you do not have any test that is actually testing number 3, because number 3 is never used in your tests. Code coverage tests can tell you that. And ideally, you have a code base where you have at least 90 to 95% of the source code lines actually in use by your testing data set. And there are also automated tools for that. If you want to know, ask me or just look it up on the internet, but there's a ton of tools out there, some of which are always, already integrated into LLVM, for example. So there's very little overhead here. And they produce nice HTML output and whatever. Yeah, and on top of all, obviously, use source version control. Please don't, I don't know, save folders with, I don't know, timestamps and the suffix that tells you which feature was added at that point and so on. Ideally, just use Git. If you don't like Git, use something like Subversion or something, but Git really should be the standard for many years now. So really use these tools that are available, because in the beginning it's a pain to get yourself used to that, but down the road you will just save time. And trust me, as I said, we used all of that in a C++ project of, I think it was 150,000 lines of code, or 200,000 maybe, with a lot of template code going over 10 years, and this is extremely important. And why I stress that so much is because I have this, or we have this experience, and to show you what this looks like in the real world, I present you with the best of real commit messages that I personally encountered or my colleagues encountered in the past. All of the strings that you see up here are actually copy-paste from the log of Git repos. It could even be the same repo. I can't remember if I added some from another repo. I'm not going to tell you who committed these. Those are various people, but yeah, let's just go through this. So on the left, obviously, there's the don'ts. There's the list of things you should not do. So the first commit I found was stuff, even with capitalization error, although I really don't care anymore at this point. This doesn't tell you anything about what happened in this commit. I need to look at the diff, I need to look at the lines that were touched, the files that were touched. Never ever commit something like this. This really straightforward just shows you do not care about your colleagues that are co-developing in the same code base. And even this shows you do not care about yourself, because if you debug something in this code base and you think, okay, it worked at some point, it stopped working at some point, I need to look at my commits from 1 year ago, you're not gonna have any idea what you did back then. The next commit was manager stuff. Manager is a component in this repo. So, okay, you know something happened in this component. The component consisted of a few thousand lines of code. Well, thanks for that. The next commit was actually more manager stuff, which followed at some point after manager stuff. Doesn't help. The next commit was make things work. I'm at a loss of words here. The next one I selected. So obviously those are not consecutive or contiguous commits. There was some stuff happening in between, and some of the commits were actually normally named or named in a useful fashion. Those are really the worst that I could find in the first 5 minutes that I spent on this. But this should never, you should not find a single commit that looks like that, not a single commit message. The next one shows that somebody was apparently trying to learn how to use Vim, because the actual commit message consisted of 2 colons a W, 2 colons a Q, and then merge branch master, which is usually the comment that Git tells you in your commit message editor. So if you don't know how to use Vim, that's perfectly fine. You can also commit using Emacs. You can commit on the command line, just specifying the message using -m. You don't need to use an editor for that. But if you don't know how to use Vim and you happen to save such a commit message, please don't push it. Please do a git commit amend and change the message before pushing. And yeah, the last message, I have no idea. I think somebody was just hitting keys on their keyboard because they were bored. This is an actual commit that I found in a code base. Moving on to how they should actually look like. And you're not gonna get too much information, for example, from the second one, because you have no idea what the repo is about, what the project was about, what the specific component was about. But if you had worked in this project, you would have a very good idea of what happened. So the first commit says added performance fix. So it's something non-functional here. We're not talking about bug fixing. For data item manager get, which means we know the component and we even know the function of the component that was changed. By caching fragment result in reference. That doesn't tell you too much, but at least you know some caching is going on. So if you happen to have a program where at some point it was computing correct output, and after this commit it started to partially compute incorrect output, it could, for example, have to do with this caching. Maybe you cache old, obsolete values or something like that. So this really tells you a lot without having to look at the diff, because the diff could be a single line, but then again it could be 500 lines. And I already, without looking at the files, without looking at the diff, I already know what component was touched, which function was touched, that this commit should not affect the result correctness at all. If it does, it's definitely a bug, and so on. The next commit message, remove debug print statement. Doesn't tell us really where it happened, but usually removing debug print statements means somebody forgot to disable some debugging print statements when they were committing the code. They were debugging and they left the output in there. This happens all the time. And those I think are fine, because usually if you run into debugging or you run into errors of your program, you don't care about the debugging output that the program made. So usually I don't see the point in elaborating where this happened, for example, although you could put additional information there. Fix the linking issue of the unwrapped tuple function. Doesn't give you a lot of information if you don't know the project, but if you do, then why not? It's just some makefile editing, if I remember correctly. Redirect the system output, runtime system output to error stream. Straightforward, tells you what happened. At some point you ran your program, you were doing some pipe redirection, and you are missing the entire output. You immediately know why this happened, because somebody switched from standard out to standard error. And fixing typos. I think I'm fine with stuff like that, because yeah, fixing typos is a language thing, and unless your repo is really centered around language documentation or an actual document for which you need to track where a typo was fixed. If this is just a comment in a code base, then obviously this is sufficient. So, but just to give you an example, the ones on the right are good practice and the ones on the left are extremely bad practice, and stuff like that should never happen. Okay. In general, I rarely give reading recommendations or reference material, but I can really recommend the Clean Codebook by Robert Martin. Put the ISBN up there, so it's extremely easy to find, but also the cover is quite easy to recognize. It's also available in German translation, and it holds a lot of information about how to write clean code, how to name your functions, how to name your identifiers, what functions or what portions of code should append in its own function, whether you should use flags or structs or templates or overloading in order to differ between different variants of your functions, how to assemble your data structures, how to write unit tests, and all of this stuff, how to even refactor your code if you want to move from a bad code base to a better code base, how to do this refactoring process. So I haven't read the entire book. It's too long, but I read a few chapters and I think it's quite good. So if you're really interested in improving your coding skills in terms of writing clean code, writing maintainable code, I can really recommend this reading material here. Now, moving away from coding guidelines and moving towards actual debugging guidelines. So what you always should do, and this sounds extremely simple and straightforward, but it's very important and still people often get it wrong. Try to create a minimal working example, an MWE. You see this request all the time online on Stack Overflow if somebody posts their university homework, for example, and they say, okay, this doesn't work, can you please help me? And then they paste 300 lines of code. Nobody on Stack Overflow is going to help you there, unless that's actually the minimum amount of code required to show the bug. So what you should do is try to minimize the problem size. You should try to minimize the components or the features that are involved. You should try to ensure that it's reproducible. And if you cannot do that because your algorithm is inherently non-deterministic, at least try to increase reproducibility. Maybe there's some corner case where it happens more often than for others. And if you work with parallel programs, try to minimize the machine size, for example. Ideally, the bug already happens with a single process or a single thread. Because in that case, it's much easier to debug. You can just omit the entire parallel thinking. Even if that's not the case, it's easier to debug a parallel program where you have a bug occurring with 2 threads compared to 64, because it's simply less context that you have to keep in your mind. And also try to minimize the complexity of the parallel interaction. So if we deal with multiple communication patterns, where we have a communication pattern that's easier and to understand and one that is more complicated, and the bug occurs for both of them, for example, try to stick to the simple one because it's less stuff that you have to consider. And basically all of these dive down to minimizing, and I cannot stress this enough, debugging feedback cycle times, which means how long does it take for you when you make a code change in order to try to fix your bug until you get the information whether the bug was fixed with that change or not. Ideally, this time should be as short as possible. Ideally, if I hit the keys and I finished implementing, I immediately want to see whether this works or not. Obviously, this doesn't work because we need to compile our program, we need to run our program, but still we should try to minimize these times. So that's why I'm saying minimize the problem size. If you have to wait for 10 seconds, for example, to know whether your bug is still apparent, it's probably already too long. I personally get annoyed if it takes 5 seconds already. 1 or 2 seconds is, that's just my personal preference. 1 or 2 seconds is okay for me. But definitely if it takes a minute or longer, this is much too long. This is gonna, if you have to do 30 cycles, this means at least 30 minutes just of evaluation time without actually coding. This is not useful. It also reduces the amount of memory you need to inspect. So if you have a problem size of a few gigabytes of data, and the bug also shows up if you only work on a few kilobytes of data. It's much easier to inspect a few kilobytes of data in your debugger, for example, compared to gigabytes of data. It just doesn't make sense to work with more than you need. It also reduces the amount of code to consider. If we now move to the second bullet of minimizing software components and so on, try to remove all the components that you think are not contributing to this bug, because you then can simply ignore them. And in general, this also reduces the overall complexity of components interacting, both in a parallel and a non-parallel context. Think about a component generating output data that is then ingested as input data by a second component. This is an interaction, even if this entire process is sequential, right? And you try to minimize all of these complexities. And I even put it here as a bullet. This sounds really simple, but don't underestimate this. This is really quite important. A small note even about minimizing the debug feedback cycles. Also try to play a little bit with compiler flags, changing between 03 and 00, for example, to see if the bug still occurs. And if the bug also occurs with 00, for example, then it's easier for you to debug because first of all, you probably, I will have this on a later slide, have an easier time debugging your source code because you have more information of where you are in your source code and your binary, because all the compiler optimizations that remove code and rephrase code and so on, all of those optimizations are gone. And second of all, if you have very complicated codes that require expensive optimizations from the compiler, changing from O3 to O0 can actually reduce your compile time. And if your compile time makes up a large portion of your overall feedback cycle time, then this should also be reduced. So this is unfortunately a trade-off, because if we switch from O3 to O0, we save compilation time, which is good. But if we run then with a program that was compiled with O0, we probably increased the runtime because we disabled optimizations. So you decrease one, you increase the other, and it's basically on a you have to decide on a use case basis which is more beneficial to you. Most of the time, the compile time is not that long if it's not some complicated C++ code, and the execution time is really what you want to go for in minimizing. But I've already worked with large code bases where you actually have GCC processes that, I kid you not, that run for 20 minutes. A single translation unit, 20 minutes of compile time. If that happens, obviously you also want to reduce the compile time in order to debug. So yeah. And consider for all of that, not only, if you do all of that, not only do you arrive at a minimum working example at the end that is nice to present to colleagues and to discuss, but also every change along the way towards this minimum working example gives you more information about the problem. I reduce the problem size. Does it still occur or not? I remove the software component that is no longer involved. Is the bug still there or not? And even the compiler flags, for example, if you have a bug that appears with O3 and does not appear with O0 or the other way around, it could, for example, simply be undefined behavior because the compiler makes some assumptions with O3 and does not with O0. So it could be some uninitialized variable or some other undefined behavior context. So all of this gives you more information about your problem, and you might recognize or you might notice that none of these really dive into using some specialized tool for parallel debugging. Could be quite boring to you because you expected some magic tool that does all the work for you, but these things are really basics, they are really important, and they help you much more than trying to find some tool, learning how to use the tool, and then trying to use the tool output to fix your code, because the output from the tool could also be wrong. I will show examples later on where these tools that are available sometimes get it wrong and don't really help you at all. Moving to some of these actual tools, let's first talk about serial debuggers. So the most important ones are GDB and Valgrind. So GDB, you should know both of them, still quickly gonna go through them. GDB is very useful for inspecting memory contents, getting call stacks and so on, inspecting data. And most people only use it for sequential programs, but obviously it also works with multi-threaded programs and also MPI. When we deal with MPI, we have multiple processes. When we deal with multi-threaded programs, you might need to be careful about when you start debugging your program and you run expressions in GDB that GDB can basically inject in your binary, right? You can print something, for example. You should be careful whether you want to stop the remaining threads of your program. So if you really do multi-threaded program debugging using GDB, read up a little bit on the specific flags that GDB offers for this case, which mostly have to do with scheduling of the threads that you are not currently looking at and that might still sort of run in the background. I'm just going to leave it at that, just to make you aware that if you do that, there's a little bit more information, and look it up. If you use MPI, for example, you might think of, okay, how do I run this with GDB? Well, first of all, GDB can automate commands. So I have an example here where we're simply running a program with MPI exec, giving the number of processes here or the number of ranks, running GDB, and then with minus EX tells GDB to execute a certain command. In this case, we tell GDB when it starts up, first, I want you to execute run. I want you then to execute BT after stopping for some point. So obviously these will not run immediately, but after running, GDB will only execute the next command if it stops at some point. Could be a breakpoint, could be some seg fault, whatever. As the next command, simply issue a quit. And afterwards, of course, the program binary as you would normally do with GDB. If you run this line, and if you do a little bit of, for example, slurm magic or bash magic, you can redirect output into, for example, separate files per rank or per node, and then you will get a full stack trace of each stack of every of every of your MPI processes. You get every stack of an MPI process in your entire program. And this will immediately give you an overview of, for example, when you run into a seg fault because you sent null pointers at data or whatever you did. Will give you immediately an overview of where every rank was when this happened. It's extremely simple, but it's a very useful tool. You can also debug, for example, a single MPI process, because I mean, this could still assume we have 10,000 ranks. You don't want to look through 10,000 profiles, obviously, or call stacks. You could also use with OpenMPI. I don't think this is part of the MPI standard actually, but OpenMPI at least supports it, that you can differ between how binaries are started or how the binary is started for the same MPI process, for the same MPI program. So here we have the line MPI exec minus N1, which means start only one process with GDB and our process, our binary. And the column then says, okay, there's going to be a next sort of sequence of commands. Start x minus 1, so all the remaining ranks without GDB, just running the binary as it is. And this even allows you to do, for example, interactive debugging. If you have a low number of ranks, like 2 or 3 or 4, you could even do interactive debugging for all of them, assuming you don't run into some kind of timeout and if you can type fast enough and stuff like that. But most of the time, this is not an issue. So you could look at the program for minutes before a runtime decides at some point that something deadlocked. There's nothing in the MPI standard that says your program needs to be responsive to the MPI library or something like that. And this allows you to, for example, just look at a single rank, a single process, do stepping, look at variables, inspect memory, and so on. And of course, most of you should know, you can even attach GDB to already running processes by just providing the PID. But in a cluster context, this is probably a little bit more difficult because you usually don't have direct access to a node where your job is already running because it's exclusive only anyway. Some clusters have specific debugging jobs that allow you to basically, again, submit an interactive terminal to a node where your previous job is already running just for this exact purpose, but many clusters don't. And for that, you need to use some batch debugging, as with the previous two examples, for example. And the second tool that's really important is Valgrind. I'm specifically calling it Valgrind or Valgrind. It's not Valgrind, as many people think, because the name comes actually from Nordic mythology. If you're interested, read it up on the FAQ of the Valgrind or Valgrind website. I think it was the main entrance to Valhalla or something like that. And there are animals on top of the entrance that only allow the worthy to enter or something, and that's why they, basically weed out the bugs in your program. So it's mostly a tool for finding memory leaks, but it has more functionality than that. It's just that the memory checker is the standard tool that you run if you run this tool without any additional flags. Besides, however, the memory checker, it also has cache grind, for example, which is a cache simulator that tries to predict the number of cache misses if you specify the associativity, the size of the cache, line size, and so on. Or it can generate a call graph for you. But we will see more tools for that later on. Valgrind can also work with multi-threaded programs, but you need to be careful. There's no longer any parallel execution happening here. So this is more like concurrent programming, because Valgrind will, in order to execute another thread, Valgrind will stop the current thread. There's no real parallel execution anymore. Many people say it's very ill-suited for parallel debugging, debugging multi-threaded programs. Personally, I disagree, because even executing parallel programs only in a concurrent context, not really at the same time, still gives you a lot of information, still can show you race conditions, can show you undefined behavior and so on. I still think it's a quite important tool, but you should be aware, because of this sort of sequentialization, this concurrency instead of full parallelism, it can really slow you down a lot. If you have 64 threads with a really nice CPU time, wall time relationship, that means using Valgrind just for this very fact already increases your execution time by a factor of 64. Not counting the general overhead that you get with the tool anyway, because it needs to check every memory access, it needs to check synchronization, and so on and so on. And also be careful, because it can yield false positives. For example, if you use thread local storage with OpenMP, you might get some output. I think we already saw that also with OpenMP. You get some OpenMPI. you get some output that is not necessarily correct. So this is already where tools start to fail us, and this is why we have to pay more attention to the code that we write instead of just taking the output of such tools for granted and just sticking to them without doing any sanity checks. Beyond these two tools, there are also compiler sanitizers that we mentioned once or twice, I think. This still mostly deals with serial stuff, but also, I mean, obviously all of this applies to multi-process programs like with MPI, and most of this also applies to multi-threaded programs. It's just not specific for parallel execution, but that doesn't prevent you from using it in such a context. Sanitizers are tools that instrument code at compile time in order to then perform some checks at runtime. For example, the compiler knows that a certain operator in C is not allowed to, or is not specified to take negative operands. This is usually never checked at runtime. It simply generates instructions that simply throw the operands at this operator, and whatever is the result is the result. If it's undefined behavior, it's your fault, because you should know the C standard. However, here, if you enable sanitizers, the compiler will actually add checks that, okay, this, for example, is an operator that does not allow negative operands. So before that, I will put an instruction there that checks if any of the operands is less than 0. If yes, at runtime, you will get a runtime error or a runtime warning that tells you this operator in this line is getting data for which it was not specified. Quite useful. I ran into this myself, actually submitted a bug for GCC after, I thought I had a wrong program or a wrong compiler binary, or a binary that was compiled in the wrong way. Submitted or tried to submit a GCC bug. The very first suggestion was run this sanitizer, and I figured out that I'm using the bit shift operator with a negative operand, which is not allowed. And I didn't know before, to be honest, that the code was doing that. The advantage of these tools is that often they have lower overhead compared to external tools such as Valgrind, because they have the knowledge of the compiler, and the compiler can statically decide, can something happen or can something not happen. If, for example, I use a bit shift operator, and I'm using a variable as the operand, however, that is somewhere defined as a const int or even as a const expr, for example, in C++, somewhere in the code, and the compiler can do this value propagation, constant propagation, the compiler will know that this can never be a negative value, so it's not going to put a check there in any way. By doing this in the compilation process, the compiler can omit these runtime code insertions at positions where the compiler knows this can never happen anyway. Statically, it can already never happen, so why would I again check at runtime? Tools such as Valgrind don't know that, so obviously they have to check for basically everything. And obviously Valgrind is not going to help you with misusing the C language in terms of, for example, a negative operand with the bit shift operator. Something like that Valgrind will not identify. If you are not sure that you're really catching all of these bugs, simply try to use multiple tools. For example, use address sanitizers of multiple compilers potentially, if you can spare them. So, for example, LLVM or Clang and GCC or the IBM compiler, whatever you use. And Valgrind, for example, and simply compare the results. If you want to do a majority vote, for example, if you have 3 of these tools and 2 of them tell you there is an issue and the third one doesn't, potentially there is an issue. If it's just 1 tool out of 5, it might just be a false positive. And even, for example, try to switch the entire platform. Try to include, if you can afford it, Visual Studio in your compilation and your testing, because it's not only a different compiler, it's a completely different operating system. That tells you a lot about the problem that, or the bug that is actually happening in your code. And depending on the compiler that you're using, you might have multiple sanitizers available. There's address sanitizers, for example, for buffer overflows, for using data or using memory allocations that were already freed. Corrupting your stack, for example, if you have a printf with more format specifiers than you actually provided variables for in the function signature, obviously you're corrupting your stack with that, and so on and so on. Or even mismatching data types, printing a single byte with a printf, but the variable that you provide is actually a full 64-bit number or something like that. If you don't exceed this for too much, then probably this will be hidden by some automatic padding anyway. But if at some point you do this for 128 bytes or 256 bytes, you will definitely corrupt your stack by a lot. Then there are sanitizers for undefined behavior. For example, for overflows, for floating point division by 0, negative shift operands, which is the one that I personally ran into at some point. There's a thread sanitizer for detecting data races. There is a leak checker that can detect memory leaks, which is basically the same as the memcheck tool of Valgrind, and so on. So I'm not giving a complete list here, not even specific names, because all of this really depends on the compiler that you're using, just to give you an idea of what's out there. Next to that, we have call graph generators. So there are many tools available for generating such call graphs, and this can happen either statically at compile time, or it can happen dynamically at runtime. Statically, there's Doxygen, obviously, there's opt, there's cflow, and so on, and those are sort of limited because they only have the static information available. You would probably know, okay, which class is a subclass of another parent class or something like that in terms of inheritance, but it doesn't really tell you anything about from which context was a certain function called if there are 5 possibilities. You will just know that there are 5 possibilities, but there's not any runtime information going on. For dynamic call graph generation, you have gprof or callgrind, for example. There's OpenPet, ppprof, code analyst, and so on. There's many more tools. I'm not listing all of them because there's a ton of them. And also, most importantly, most performance analysis tools that we're going to discuss in a few minutes also provide some form of this call graph generation, because usually you need a call graph in order to realize where you are, how you got there, in what context you got there. And it would just be like debugging your program with GDB. You only get the current function, don't get the entire backtrace. You don't get the call stack, but only the last frame that you're currently in. This is very limited in its usefulness. So that's why most performance analysis tools, even with graphical user interfaces and so on, they still provide functions for generating such a call graph because it has such a high importance. Yeah, then moving on to parallel debuggers. The issue here is that there's very little free software, unfortunately. There are 2 commercial top dogs that I personally am not using. DDT from ARM, which used to be Alinea software or something like that, but ARM bought them a while ago. And there's TotalView from RogueWave software. I know that these are used in larger supercomputers and clusters. I don't advertise their use here. I will have 2 screenshots from DDT, for example, to show you what to expect if you use such a tool. But they are sort of expensive. I think, I didn't check recently, but a few years ago, a license was at least a few €100 per year. And I don't like to advertise commercial software in my lecture at the university unless there's a very, very, very good reason to do so. I'd rather prefer open source or something like that. So just to tell you, it's out there. You can read up their marketing descriptions on the websites and so on. And I'm not saying they're not useful. I'm pretty sure they do a good job. They just ask you for quite some amount of money. They do support OpenMP, MPI, CUDA, and so on. And in addition to sequential debuggers, they have some additional features that are really centered around parallelism. For example, and I will show you illustrations of that in 1 or 2 slides, you can examine variables per thread or per rank and compare all of them across your entire program. You can examine, for example, the send-receive queues of MPI libraries to see if you, for example, if you have an overproduction of messages that are sent or received, and that might not even be your functional problem, but your performance problem, for example, and so on. But still, for very, very large programs, the usefulness can be limited, especially if you don't have any help from people that are used to debugging these large problems. So if you start to run your very first program on a large supercomputer with 10,000 ranks, and you try to use one of these tools and you don't have any additional help besides some documentation, you might not get very far. It really takes some time to get used to debugging these large programs and getting to know what to look for. So I promised visualizations, and here they are. So this is an older version, but that doesn't matter, of the DDT tool, which shows you centered the source code, which is obviously the focus of our attention. On the left, you simply have a source code file listing, just like you have with normal code editors. And what's important here on the top, for example, is the range of ranks that you have from 0 to 11. So we have 12 total. And you can simply, for example, debug a source code line where we say we're interested in the data of the variable mype, for example, mype, whatever that means, I have no idea. And on the right, we see that for the current line, what variables do we have at the moment for this current rank. In this case, it's rank 0 that is selected. And you can just quickly step through all the ranks for the same source code line and check what is every process's value for that. In this case, it's even a Fortran program, apparently, because this is not C or C++ code, and we have a .f file ending, so I'm very happy about that. And below here we get a call stack. Obviously, you can also see we have the ability to set watch points, break points, and so on. So this is really like a normal debugger. At least this view, this tool set here of the DDT tool is like a normal debugger, just enriched with the knowledge that we have a parallel program and we want to have this information per process only, not just a single time. The next visualization I want to show you is on the left, communication pattern, for example, where you see individual send and receive calls and how they match up with individual ranks. You can, for example, select if you want to show local rank or global rank IDs. You see, this is probably, I'm not entirely sure, but I think this is the number of messages that is exchanged. You can switch between which communicators you want to look at, because as you know, there could be a lot of them. This could be, for example, a library, because as I told you, the first thing you do as a library, always create a new communicator, because you might be running in a parallel MPI context of the parent program that is using your library. So this is probably this MPI-com self communicator here. And you see all of this is really geared towards debugging MPI programs. But again, it's commercial software. And on the right, something that I think is a bit underestimated, but is a really nice tool, is the data inspection of local variables. And obviously, I mean, for a current rank that you selected, you see the immediate numbers that you have here. But what you see is also a tiny illustration of the data of this variable across all the ranks. So this is basically always a graph or a figure where on the x-axis you have the rank ID and the y-axis is the value for every rank. And you see obviously the number of arguments is the same for every of these process images. Probably this should be the case for all of them, otherwise something is going wrong with your argc value. But also, for example, we see that my rank is probably the variable that should hold every rank's ID, and of course, obviously, it's a linear function of x equals y or y equals x. And with this visual representation across ranks, especially if you have such linear relationships, I think it's quite easy to figure out that something is correct or something is wrong just by looking at how the line goes in the figure. So I think this is quite a nice idea, and this is quite old. They did this already, I don't know, many, many years ago. And this is just to show you what small tools you can use for parallel debugging if you really want to work in a parallel context. But then again, as I said, it's a commercial tool, unfortunately. So this is why I didn't tell you to use it earlier for your programs and so on. So moving beyond this visual inspection, going towards fully automatic tools, there are also tools that can do automatic race condition debugging. And this is quite, a tricky topic. This is very difficult to do automatically and exactly, or in an authentic way. Because statically detecting race conditions obviously doesn't work. If that would work, we probably would have solved, I don't know, the halting problem by now. You can't just detect any race conditions statically because you don't know what's happening at runtime with the scheduling, when which thread will be suspended by the operating system because the operating system decided that it needs to do some logging, writing to the disk and so on. All of this information makes the performance of your program non-deterministic and makes data races non-deterministic. Dynamically detecting these race conditions is possible, obviously, but incurs a large runtime overhead because you need to check every memory access and you need to check, did any synchronization happen in between? Is the synchronization really securing and safeguarding this critical region that I had before, and so on and so on. All of this must be logged, all of this must be checked and computed against each other, and this has a lot of runtime overhead, as I will show you in a bit. That's the reason why most of these solutions resort to using heuristics instead of using exact or analytic approaches, because they are simply not feasible. Either because we can't do them or because they would take much too long. If your program runs longer by a factor of 1 billion, you cannot any longer debug your program, right? That doesn't work. Using heuristics now, there are several experimental tools available in research or in academia. And all of them have mostly the same issues of very limited scope, for example, which means you cannot use the full programming language. There are certain features of the programming language that you're not allowed to use, like virtual function calls in C++, for example. Or it could be that a program works perfectly, but it only works to stencil kind of codes where you have a perfect loop nest and you don't have any instructions that are not perfectly nested inside a loop, or you don't have any instructions next to a loop inside a loop nest, stuff like that. If you go to very generic programs that can use everything in the C language, everything in the C++ language, and so on, the amount of tools that actually can work is reduced to a bare minimum, and even then you do not always get the results that you wanted. So one of these tools that is quite mature and I think is still free is the Intel Inspector, for example, which I will show you now. I have a few screenshots of the Intel Inspector. I used to show this live in a lecture hall. I didn't set it up now at home because I simply don't have it installed. It's a few gigabytes of stuff that you get in, and Visual Studio plugins and so ever. It's just it's nice because it's free. There's a Linux and a Windows version, and the Windows version, for example, integrates nicely with Visual Studio, and it claims to be able to automatically find bugs in multi-threaded programs like deadlocks, like memory corruption, race conditions, and so on. And it can do that for OpenMP, for Intel thread building blocks, for P threads, for Windows threads, and a few others, but that's mostly it. And you do get these features, at least most of them, to some degree. But there are also quite some severe limitations, at least in my opinion. So first of all, this tool also suffers from this slowdown. If you run your program with the Intel Inspector, you can select how much it should check your code, so which features should be, or which type of bugs should be detectable. And by adding more or more complex bug types, it will increase the slowdown factor. It even shows you an estimate that, okay, it thinks it will slow down your program by a factor of 60 or a factor of 200 or something like that. And this is not specific to your program. These are just generic estimates of what people are used to. So on average, if you enable this feature, you incur a slowdown of a factor of 300, for example. And this is not, this is just a ballpark number, but I'm not making this up. It's really, the standard setting, I think, is about 160 times slower or something like that. Or at least used to be in the version 2 or 3 years ago. They only claim explicit support for Intel OpenMP. Does not mean they don't work with GNU OpenMP, for example, but you don't get official support for it. But I already did debugging with GNU OpenMP, and it works to some degree also. It can do error detection only at runtime, so no static checking. You actually need to run your program, and only in executed control flow branches, which is different compared to sanitizers, for example, or code coverage tests and stuff like that. Everything where the compiler is involved, the compiler can already check, can this code be visited or not? If the code is not visited statically already, it cannot be the cause of your bug, obviously. This tool can only check, because it's a runtime tool, all the constructs, all the source code lines that are actually executed in your control flow. If you want to execute a different control flow, you need to change your input data, for example. And unfortunately, it can provide false negatives and false positives. And I'm going to show you some examples. So let's take a very, very simple, naive OpenMP program where we try to have a loop parallelized, and I want to increment some counter in parallel. And as you all know by now, by default, counter is a shared variable. Because we're in a parallel context, there's no data sharing clause here, so counter is shared. We increment it inside a parallel loop, and obviously there's going to be a data race. It might not happen for only 10 iterations, but just for simplicity, I put 10 there. If we run this now with the Intel Inspector, and we are, I think I took this from Visual Studio, so you get this nice graphical user interface that highlights code and everything. We get the output that we see on the right, and it tells us there is a race condition in line 9, and it tells you more. So first of all, we have the source code line. This just says console application 1 because I was too lazy to properly name my project. This was just done ad hoc in a lecture once. Source code line 9, function main, even the module here in case you have multiple modules. And it tells us this is the occurrence of the read operation, because remember, a data race requires that you have two entities accessing the same memory location at the same time, and one of these two accesses needs to be a write operation. If any of these requirements that is not met, you don't have a race condition. In this case we do, because here we have the read, here we have the write access, and they both refer to the same line. So pretty nice, but then again, just for detecting something like that, you have to take into account performance slowdown of a factor of 50 to 100 or something like that probably. So if you have larger problem sizes, this really will not help you too much. But still, it's able to detect that there's a data race here. Now, let's assume that we don't know too much about parallel programming because we didn't pay attention in Philip's lecture, or we were bored with the entire subject anyway. We took a different course at the university, and we're still trying to do some parallel programming. Let's just split this up, because the Intel Inspector told us there's a data race in line 9 here, right? There's a read, there's a write, so let's just split these lines into two separate lines. Maybe the data race will be gone. So what do? I read the sum value into my local variable temp. This is private because it's declared inside the parallel region. I increment temp using temp plus 1, and then I write it back into sum. Because I'm incrementing my local variable, the data race is gone, right? Well, obviously it's not gone. The question is, does the tool detect it? And yes, in this case, the tool can detect it. And we see that we simply split the data race with the read operation happening at line 17. This also gives you information that it's not really temp we're talking about, because temp is not read here, temp is written here. But it's the read access, so it must be on the right-hand side of the assignment operator, so it must be sum. And the write operation, sum equals temp in line 19. So we were not able to fool our tool, there's still the data race, and obviously there is still the data race. This is an incorrect program. Now, assuming we paid a little bit of attention to Philip's lecture, we know that there is the OpenMP critical pragma, and we can use it for safeguarding critical regions. Let's simply say we have the program as before with our temporary variable, but I now safeguard the reading of sum and the writing to sum to be mutually exclusive. I have a critical region here. I do not give any name, which means they both have the same name because it's the empty string, evaluates to the same, which means they are mutually exclusive. So I can only at the same time read from sum or write to sum, but I can't simultaneously do this. So the data race should be gone, right? The problem is, no. This is still an incorrect program because this does not fulfill the transactional properties of such an access. It's not atomic because I'm still having separate operations for reading and writing. The increment is happening in between, and you could have 4 threads, for example, that all first read the sum value, all do the local increment, all write the sum value back, and at the very end, sum will have incremented by 1 only, not by 4, because we had 4 threads. So this is not atomic. This doesn't help. You need a single critical around the entire thing. And this is not detected by the Intel inspector. I have to admit, this is a little bit, in 2020 doesn't sound too old, but actually I think nowadays they already offer the 2021 version. I did not check. I only checked this last year for the lecture with the 2020 inspector, where I actually demonstrated this live. Maybe they fixed it. I know it was broken already for a few years. I know this has been broken for at least 5 years or so in several versions. That would rather lead me to believe that they still didn't fix it in 2021. I also don't know the complexity of finding something like that out at runtime. I'm not really that kind of guy. I'm more the program development guy and not the tool development guy here. But could be that they fixed it in the 2020 version, but it still shows you it's quite a short source code. I think it's straightforward why something like that cannot work, because the reading and the writing needs to be happening in the same critical region with the same atomic operation. And as soon as you do one read, nobody else is allowed to do a read until you wrote back your increment. This is violated here. It's only a few lines of code, and still this quite large tool, it takes a few gigabytes to install if I remember, is not able to detect that. So don't trust those tools, and that's why I'm telling you, try to really stick to coding guidelines, try to do all the unit tests, continuous integration, code coverage, and so on. All of this usually helps you much more than using such a tool as Intel Inspector, waiting for 2 hours until it finished your real-world problem size, if it only takes 2 hours, and then going through the output and realizing that half of the results are false positives, and the actual bug that you were looking for was not found. Who knows? But go ahead and try yourself. So I'm not telling you not to use the tool. I'm just saying be aware that these are not really the do-all tools. And beyond that, there's also domain-specific debugging. So everything we talked about now is really generic, but you could also simply visualize the output using appropriate tools like gnuplot or PowerView, for example. On the right on this slide, you see several visualizations that we already saw, I think, in the motivation lecture in the beginning. Our nose wheel of Boeing airplane, then the solar wind particles that hit Earth's magnetosphere, and the lowest one was the weather prediction of ZAMK for the day of the lecture, I think, which was probably beginning of October, can't remember. And the good thing about those is humans are well trained in finding those issues in a visual way. If I see some error in performance turbulence, I mean, in this image, it could be quite difficult to see, but if my program calculates the performance turbulence is happening in front of the nose wheel gear, like 1 meter in front, probably your program is doing something wrong. And we are quite well versed in seeing stuff like that and identifying errors like that very, very quickly. Just like you know how to tell a cat from a dog or a dog from a cat. So the downside of that is, however, you need to do this yourself. This cannot really be automated. We might have AI systems that can, I don't know, drive cars, and we might have AI systems that even can tell a cat from a dog. But this really gets complicated at some point, and very often when I work with domain scientists, apart from the fact that these machine learning things are not really in production use yet, at the moment we're still at the stage of demonstrating what this technology can do. It really still resorts to domain scientists that look at the output and simply tell me, for example, as the computer scientist, Philip, I tell you this is wrong. I can't tell you why it's happening, but this curve should not look like that. Physics doesn't behave like that, for example. So whenever it's feasible, prefer unit and integration tests because those can be checked automatically. And you can have integration tests that waste CPU hours and CPU hours overnight or even during the day if you have your separate CI system that do all of this checking where you don't have to spend any work on that and simply afterwards see that there's an assertion that failed and you know which value was wrong. If you need to look at images, you really need to spend the time yourself. So, yeah. So sort of concluding this portion, the best approach to debugging parallel programs is really know your algorithm and know your implementation. Like for example, a statement that should already tell you something because we had it in our pro seminar and the lecture. Know that your program is doing an n-body simulation using a Barnes-Hut implementation. Then you immediately know, okay, there's some bounding volume hierarchy thing going on and we have particles that are exchanged and so on. You already sort of can set your mind to what could go wrong with something like that. Next, also know your programming models and your languages, and especially their hidden semantics. For example, one of the more complex ones, at least in the scope of this lecture, you have a thread private clauses in OpenMP. And for thread private variables, the data persists between threads or per threads between parallel regions, rather, if parallel regions are executed using the same number of threads and the same affinity policy, in this case static. If I have one parallel and I have a second parallel, then the thread private data per thread will survive these parallel regions, even if between the parallel regions you can't access the thread private data because you only have the master thread. This is something you need to know about OpenMP. You might run into this at some point. Or let's go to programming languages, knowing that the destructor of a C++ object will be called at the end of the full expression where this object was created, for example. This is something you need to know about C++. If you try to use the object again within the expression, for example, within the full expression, there's no problem. It wouldn't have been destroyed yet. If you use it after the full expression, it's a user after free, essentially. And in general, don't trust seemingly automatic tools. Don't trust them too much. They can be useful. They're nice to try out. But in my personal opinion, dealing with larger code bases, dealing with larger programs, also in a parallel context with regard to how many threads you have or how many ranks you have, it's usually much better to just really know the source code and really, this sounds tedious because it's a lot of effort, but that's really the thing. And you can't use a tool for debugging 10,000 threads in 5 minutes and find your bug. It simply doesn't work that. In my experience, it's rather easier to just know what you did and stick to clean coding. With that, we're done with the functional debugging. Are there any questions so far? Nobody seems to be typing, so I hope you are all happy so far. I will just continue in this case. Anyway, we can have questions at the end. Now, performance debugging, people also sometimes like to call non-functional debugging because it's not centered around the functional output, the functional usefulness of your program. It's around everything else, as in how long does it execute, how much energy does it consume, and so on. Mostly it's about execution time. It's not always only about execution time, but still that's the first class citizen in HPC and in parallel programming. So for the sake of this lecture, we're only gonna deal with execution time. It's more tricky than functional debugging because for functional debugging, you know when something went wrong. If your program crashes, you know without anybody else assisting you. If you get wrong output, you need to know something about the semantics and the content of your program, but you still will have the information something went wrong. With performance, if you have a performance bug, how do you know there is a performance bug? How do you know that your program is slower than it should be? And when do you know that this performance bug was fixed? Because it's faster now by 20%? Should it be 20? Should it be 40? Should it be a factor of 5? Much more difficult, right? Most aspects of functional debugging or also sequential programs still apply. So writing clean codes, writing codes using best practice policies, using all the toolchain features available like warnings and so on, all of these also help you with performance bugs. Especially because if your code does not adhere to these guidelines and you already have functional problems, I would not dive into performance because it doesn't help you if your code computes very fast the wrong result, obviously. So first we need to make sure it runs correctly, then we need to make sure it runs fast. And also for running fast and finding performance bugs, you need to read and maintain the code. So all of the previous things still apply here. Add to that even more so the importance of reproducibility, for example, fixing random seeds, fixing scheduling affinities, because if you run your programs 5 times and you have a really, really large standard deviation, this really makes it difficult to debug the performance because you don't know how long it takes on average maybe, and you need to use some statistical means and so on. So try to make it as reproducible as possible. If required, you could even have performance unit tests, for example, and performance regression checks. So you can have tools that where you write tests, and for every test you add the information, this should run on your known CI hardware in about 5 seconds. If it takes at least a factor of 2 longer than that, you should raise a flag and send everybody an email, for example. There are tools out there that can do that, and it's really useful to know not only that a commit did not break a repository in the sense that it did not break the testing in unit tests and integration tests, but also that with this commit, all the tests now take 30% longer compared to what they did before. This is quite important information to have, especially if you develop for half a year and afterwards you figure out it's much slower than half a year ago. How do you find what's the culprit? Which commit used which commit caused this issue? There's a ton of performance tools available. We're going to discuss a few. And adding to all the knowledge about programming models and the languages and so on, you need a lot more knowledge about the hardware, like NUMA, false sharing behavior, cache coherency, and so on. So not going to discuss this any further because we already did so in past lectures. I want to start off with very simple tools because I think, again, they're underestimated. Top and HTOP, you should know them. They're sort of like the task manager of Linux or something in the terminal. If you don't know them, please have a look. They give you a high-level overview of the workload on the system and the components of the system. There are even some tools that show you what's the network load, what's the I/O load, and so on. And you can use this to compare to what you expected would happen. And don't underestimate the usefulness of these tools, or also the user bin time tool that we've been using a few times now. Don't underestimate the usefulness of those tools that basically ship with almost every Linux distribution. And definitely you can find a package, but most of them are pre-installed. And they're very simplistic tools. They're readily available and they can give you a lot of information. For example, ask yourself what the ratio is between the user time and the system time of your program. If the system time is too high, it could be caused by inefficient I/O, for example, because you don't do enough buffering. It could be caused by a high amount of context switching because you're using more threads than you have cores available, and so on. Then which CPU cores, for example, are you really using? If you remember, I told you it's quite difficult to check the actual affinity policy that is that your program is using or that the operating system is using, because you can only set the affinity policy that the operating system should use. Afterwards, you simply need to check which core am I currently running on, and is this the correct one? There's no real, because of the just how affinity policies work, there's no real way to verify that otherwise. There's a lot of things between affinity settings potentially in your program and your environment. Then there's, for example, the OpenMP runtime. There is the environment information set by the job scheduler, by Slurm, for example. And there is, of course, the scheduler and everything in the operating system. And through all of those layers, a lot can go wrong with affinity settings. Not mentioning multi-threading in the hardware that you can change at runtime, like you can do with IBM Power processors and so on. And last question, just an example here. What's the actual memory footprint versus what it should be? If you compute that you should allocate around, say, 1 GB of data, and you see using top or HTOP that your program uses 2 GB, probably something is happening that you don't know about. Maybe you're inadvertently using a copy constructor and the original object is not destroyed instead of doing a move, for example, or I don't know. And this is also quite useful in order to detect memory leaks, for example, without using any additional tools. Because if you have something like the heat stencil and you run it, then of course you expect the memory requirements to increase when you start your program because you're doing some mallocs, for example. After all these mallocs are finished and you're actually into the computation loop of your heat stencil, you're not allocating additional memory, so the memory consumption of your program should stay the same. If it does not, but you see that, for example, every few seconds you allocate an additional megabyte of memory, you know that you have a memory leak. And you don't need any additional tools for that. It's quite simple to see. Just run your programs for a few seconds until you think you know, or you can tell from the output that it's in its steady state where it's not doing any additional allocations, and see if the memory footprint really is constant then. Some sample output here using HTOP, which is a little bit better than top because it gives you more information in a nicer, more illustrative way, I would say. I ran this on our Hudson system, which is equipped with 2 Intel processors, 18 cores per CPU on a single node. And just using top, for example, I want to see the percentage of logical CPUs that I got. And I see I have cores 1 to 18 busy, and I have cores 37 to 54 busy, which means I'm using a total of 36 cores, right? 18 here and 18 here. So here in HTOP we can see that's the first 18, and that's the second 18, which means I'm using the full machine, and the hyperthreads 19 through 36 are idle, and 55 through 72 are idle, right? No. Because we're working in Linux, all the cores are consecutively numbered from 1 to 36, and afterwards we follow with the hyperthreads, which means I'm only using the first CPU, I'm only using the first 18 cores, but both hyperthreads of every core of the first CPU. So obviously this is probably at least a factor of 2 slower than it should be, assuming it's a computationally bound program that we're executing and not a memory bound one. Even with a memory bound one, it could be a factor of 2 because you get an additional memory controller if you switch to the second CPU. But this shows you I know something about the hardware. I know how multi-threading is represented in Linux. If it were Windows, remember, be careful because the hyperthreads are then 1 and 2, and 3 and 4 are on the same core, 5 and 6 are on the same core, and so on. In Linux, it's the other way around. And just knowing this about Linux and the hardware, and knowing how to read this very, very simple HTOP graph, I already know I screwed up my affinity mapping. Don't need to install any additional performance tool. Don't need to run it for a factor of 100 slowdown or something. That's everything. The next tool I'm not going to present in detail is perf because we already discussed it. It gives you a lot of information using performance counters like the cycles, instructions, branches, branch misses, last level code, cache load misses, load stores, and so on. This is just the default information. With -e, you can provide additional performance counters that you want to measure. Some of them are predefined, and some of them you just need to specify the exact instruction ID basically. So the instruction event number and the mask number. Not sure we discussed it here in parallel systems, but I think I mentioned it once. If you're interested in how to do those and read those, just let me know. And perf can do that. So perf can access all the performance counters that are available to you as the user, barring some security limitations in Linux that prevent you from reading model-specific registers, so MSRs in Linux. Okay. Then a little bit into terminology, which you will need for debugging tools, performance debugging tools. First of all, there's the term instrumentation, and I put it up there because many people confuse it with measurement, and it's not the same. Instrumentation is actually the process of adding source code or machine code in your program in order to measure something when it executes. This can happen automatically, for example, by a tool that does this for you, a compiler, or this can happen manually by you writing measurement statements. Like you did the time measurements, that's manual instrumentation. You start a timer and you stop a timer, you inserted the statement yourself, so it's manual instrumentation. And don't confuse this with measurement. And just to use an example, for example, if you want to know the power consumption of your TV, plugging the TV into a power meter, that's the act of instrumentation. Reading the display is actually the act of measurement. When you switch on the TV and you see that it consumes 50 watts or 200 watts, for example. And also there's the term of inclusive and exclusive measurements, which simply deals with whether we include data for regions that are nested. So here we have a function called outside, and if we take the inclusive time measurement, that means all of the time that outside consumed and all the time also of any function calls that were inside this function, including this function which is called inside here. And if we take the exclusive time measurement, that means we measure the time of both for loops, but we omit any time that was spent in another function frame, basically, another stack frame, not counting inside here. And this is important because many tools differ between inclusive and exclusive depending on what you're going for. And it's very simply explained, but it's important to know. Even more terminology, because then we're going to go into the tools, and then we're a little bit of overtime today, but I guess it's okay. We have sample versus trace-based profiling, and those are very important because they work quite differently. Sampling is a heuristic approach, which means it gives you aggregated information of how much time you spend where in the code. Because it's based on statistics, it doesn't give you exact information of the order of events or when exactly an event happened. You just get some aggregated information about how many events and how much time it did in general. And this is because it's very easy to accomplish. There's very little overhead. There's no code changes required. What you do is you execute your program. You stop the program periodically and check the program counter. Where am I in my binary currently? I write that down, I continue the program. I stop again. Say you stop every 1 millisecond, every 10 milliseconds or so. And afterwards, you build a histogram with all the program counter addresses, and you know, statistically speaking, how much time you spent where in your program. Very easy, very little overhead, and you can do with any program. If you only have the binary and it doesn't have debug symbols in there, it might not be that useful. If you have debug symbols, this is already sufficient for a lot of work. On the other hand, there are tracing tools. They produce a detailed log of which event happened at what point in time by, for example, wrapping all the MPI calls. You can simply exchange the MPI header with wrapper calls before calling every MPI function. You do a start timer, stop timer, and if you synchronize your clocks, for example, across processes or nodes, you could even establish order of events between ranks, assuming you can synchronize your clocks. The good thing about that is it gives you much more detailed information, but the downside is the overhead is much larger and you need to change the code either in binary or in the source code. For example, as I said in this case, wrap every function call. Obviously you need to insert those timer calls. This doesn't happen in the CPU in hardware. Now, one of the most important tools here is gprof. It's a sample-based profiler that comes with every GCC installation, and it's a limited code instrumenter that can also provide some call graph information and call counts, but again, it's sample-based, so all of these are statistics. They're not extremely exact. However, the good thing about it is that it's very simple in its use and it comes with every GCC installation. The only thing you need to do is compile with debug symbols, enable gprof support, which you can do with the -pg flag, run the binary as you normally would, and then run gprof binary gmon.out. Gmon.out is the output file generated by the profiler when you execute your binary. And if you want to use line resolution, this is something that people easily forget, is --line. Otherwise, you only get function granularity results, I think. And then gprof will simply tell you how much time you spent where. Let's have a look at an example. On the left side, you see source code that simply is incrementing a counter, as we saw before, in a sort of suboptimal way, because we're using a critical for that, although it's a long, and we could probably use an atomic. On the right side, we have a much more sophisticated solution for the same, where we have a local aggregation of the sum, and we even have padding in order to get around the false sharing issue, because threads would otherwise fight for the cache lines. So this should be a fairly optimal solution. We have the minimum amount of synchronization required because we don't do it inside the loop, and we also make sure that the partial sums work on different cache lines. So if we run this with gprof, then we see that, and remember that the foo function is the bad one in terms of performance, or at least we expect it to be, and the bar one is the good one, the fast one. And if we now run this with gprof, we will get a flat profile that could look like this. So here we have our function foo, here we have our function bar at some source code lines. It will give you the address back here. And it will even tell you, in this case, some specific OpenMP function that happened in line 13, which took almost all the time. It even says 100.71% because it's a statistical approach, so it's not exact. But then again, we see that line 13 was very expensive. Line 13 is exactly this line where we do the incrementation of the counter, because foo starts at line 8 and bar starts at line 19, as we can see here. So 13 is in between, and that's the counter plus of the bad solution. And we see it took basically all of the time of the program, and both functions, as you can probably judge by here, is were placed in the same executable and run consecutively, just to have the direct comparison in the same profile. And you get some additional information. You can have a look at this yourself, like the number of cores, the number of seconds required by this function only, the number of seconds required by this function, for example, and all the functions above it in the flat profile. The time per call, because those are over all the calls that happened, but in this case it doesn't matter because we only have one call, and so on and so on. An alternative are the gperf tools, which is a sample-based profiler. It was formerly known as the Google Performance Tools. And this is actually a collection of more analysis tools than just a simple profiler, but the profiler is probably the most useful one. It includes some additional tools like memory allocators, for example, that are really fast and that are geared towards a high performance context. Using it is also very simple. You simply install the library, you link with the library, and then it sort of injects some functions in your binary, and you run with the environment variable CPU profile prof.out, which means the file that is generated when running your program, the performance file. And then you run with pprof, for example, to view the results, or --gv for getting a graphical output. And to show you what this looks like, this is the call graph visualization, where again we see this is our main program. We see here gomp thread start, which is probably the parallel statement in our program. And we can see here that we have a box with a 95% of the execution time, which is line 12. Remember, gprof showed us line 13 as being the expensive one. Here it's line 12, which is just the pragma in front of the count plus plus, but it still refers to the same source code. The same location. And the other one would have been line 33, which is the good solution, and it's 0.3% only. So we would never debug something like this. We would debug this code here, just looking at the percentages. Now, beyond those simple tools, there are a lot of additional tools that you can use. And I just want to go through the list quite quickly. I don't have the time because I would need a full lecture for discussing each of them probably, and we're already using too much time today. There is the Intel pin tools, which can do dynamic binary instrumentation. So this allows you to actually put instrumentation code into your binary without recompiling. The advantage is you don't need the source code. You just really rewrite the binary. The downside is that this gives you a limited amount of information, because in a binary it's quite difficult, or it can be quite difficult, to recognize loop nests or function calls and stuff like that, and sort of refer them back to source code. If you have the source code available, then probably you could recompile and put source code instrumentation in there anyway, but still, for some border cases, the Intel pin tool exists that can help you rewrite your binary without recompiling. Because, for example, you use the library that's no longer available or something like that. Then there's Intel vTune, which is a full suite of performance analysis tools for multi-threaded programs. There's the Intel Advisor, which is an automatic dependency and vectorization checking tool, which can be quite useful. For GPUs, obviously, we have NVIDIA Nsight and AMD CodeXL for profiling and debugging on their respective GPU models. There's Tau, for which I will present 1 or 2 additional slides, which is a profiling and tracing toolkit specifically aimed at MPI and also multi-threaded programs. There's PAPI, which is not a full-fledged tool with a graphical user interface and so on, but it's a library for accessing the performance counters that you saw with perf, for example, and doing this yourself in the code. So if you don't want to resort to perf, but you want to have function calls in your code that tell you how many floating point operations did I spend, you can use PAPI for that, for example. Is perf record comparable to gperf? To be honest, Markus, I never used perf record, so I can't tell you. I'm sorry. In case you check, please let me know. I don't know. To be honest, I rarely use perf because most of the time, at least in the past, I used my own instrumentation with PAPI library cores, because I was interested in code regions and not the full executable. Then there's oprofile, which is a sampling-based profiler like you would get with gprof, for example. But it also has hardware counter support, so you get the same statistics kind of information, but not with time, but with floating point operations or with memory fetches, cache misses, and so on. And also check your IDE, because there might be some software built into it, like the debugger of Microsoft Visual Studio. I know I keep saying Visual Studio a lot. I'm not telling you that's the best developer environment. It's just that it's a really good environment for writing C++ code, really complicated C++ code, and could be one of the best ones out there, in my opinion, working with really large, really complicated C++ code bases. Doesn't mean you have to use it. Please don't take this as a general recommendation. Just I'm happy with it. It meets my needs. Beyond profiling and analyzing, there are some tools that can do pure analysis and also visualization, like Kalaska, Vampire, and so on. Not going to discuss them in detail. And anyway, this list is not complete. There are far more tools out there. Those are just really the most important ones that have been out there the longest and are most used by HPC users, I would say. Now, to show you sample output of tau, of the kind of information you can get, this is a visualization actually of ParaProf, which is the standard visualization tool that comes with the tau framework. Tau can automatically instrument your code. I have a slide on that on the next slide, I think. And the output that you get here is for every node. So a node is a rank here. You get a sort of a timeline of how much time was spent in which function. You have different colors here, and the colors correspond to the legend here, where tau application is just your overall program. Then you have a function multiply matrices, for example. You have an MPI init that apparently was quite expensive. You have MPI broadcast functions, send and receive functions. There's an SMPI init, for example, which is inside the MPI library implementation that was used. And for all of these, you sort of get an overview. In this case, it was the specific legend and the specific profile for node number 3, which corresponds to this line here. And this kind of information just tells you about where every rank is, whether you might have some load imbalance here because they don't all finish at the same time, and so on. It just allows you to establish this kind of information. And tau can also do some tracing, which means that you get really timestamp information. But again, it just introduces more overhead and gets more expensive to run that. Just be aware of that. So whenever you can be happy with sample-based profiling, stick to sample-based profiling, because it's just much faster and reduces your feedback cycle again. And just as an example why these tools exist and why they are more complicated, tau obviously has some visualization tools that you do not get with a gprof, for example. But that's not the only thing. gprof is quite stupid in the sense that it can only do the entire program and can only use the features that are implemented in the compiler, right? Tau, on the other hand, is a full-blown compiler. You can either choose to manually instrument the code, or you can ask Tau to sort of compile your program and insert instrumentation statements. And the point being that you can control the scope. On the right side, for example, you see such an instrumentation file that has a very simple syntax. It says begin instrument section, which means in between this begin and this end, you put all of the patterns or all of the information that should be gathered. And here I say I'm interested only in loops, so don't instrument anything that's not a loop. But even further than that, only loops in the file foo.cpp and only in functions that are called bar and have this specific function signature. And you can also use wildcards here, for example. The wildcards is the hash or octothorpe, for example. So I could say all the functions that start with bar, for example, and only loops inside, or only loops with a certain nesting level, and so on. So all of this information you can specify, and this gives you a finer grained control over which code is instrumented compared to gprof. And this then can make it feasible to use trace-based profiling, because you're limited to the amount of code that you're actually interested in. Trace-based information or trace-based debugging for the entire program would be much too much effort, because for every function call, for every MPI operation and so on, you have to have a timer, you need to keep a log, save the information and so on, and also sometimes this would exceed the main memory of the node that you're currently working on. But using this limitation, you can actually reduce it down to what you're really interested in and get more information out of this piece of code. And you can also limit it to specific code lines, for example, and some other stuff. I didn't show the exact usage of Tau here because it can be a little bit of a pain to install. At least it used to be a few years ago. If you want to use Tau and you run into troubles with that, please let me know. Or if you want to do a performance analysis master thesis with me or something like that, we can use these tools. And one of the last slides, I believe, the visualization of Vampire. We already saw this a little bit with the Intel Xeon Phi, I once showed you a figure. You see how much time you spend in weights, and you see how much time you do not spend in weights, but in actual application processes for a program of 16 ranks in this case. And we even see with black lines the communication patterns that show us which process was communicating with what process, or what rank basically we were waiting for. And on the right side, we see the so-called communication matrix, which is quite nice. So you see a matrix of sender and receiver, and you see the number of messages that were exchanged for every rank pair. In this case, the number is all the same. It's 2, which is why the reason why they all have the red color. But using this, for example, it's really easy to do functional debugging by figuring out that you have a few processes that are doing all the communication and the remainder is completely idle, although this is not what your algorithm should look like, for example. Or also functional debugging, if you figure out that all of them should send 2 messages and you have some ones here and green colors, that means a few send operations are not happening. Or if you have periodic boundary conditions and process 0 and process 15 are not communicating or something like that. So it's quite nice to visualize here, but unfortunately it takes quite some overhead to get these tools set up initially in order to you can use them. General hints, and I think then we're done. When you work with debuggers, of course, provide the -G flag. You should know most of these issues anyway. When compiling, if you want source code locations, and usually you do, and I mentioned it yesterday, there's very little to no performance overhead in doing so. You definitely do have a performance overhead if you switch to O0, so be careful with optimization flags, but not only because of the overhead, but also sometimes you need O0 in order to properly read your code. If you enable O2 or O3, you will have function inlining. The compiler could fuse some loops, it could split some loops, and so on. And this makes it difficult to refer a memory location or an address in the binary back to source code lines. So by disabling O3 and going back to O0, it's just easier to read the performance profile most of the time. Especially if functions are inlined and you don't have any functions identifiers anymore. If feasible, just work in O0 if you can afford it. Otherwise, try to stick to O2 or O3, but just disable the specific flags that keep you from reading the performance profile properly. Check whether any child processes are included in your analysis reports, especially with MPI, for example, or even if you do something crazy with fork and exec. Be careful about that. Check whether the tool that you're using supports actually threads. For the tools that are presented today, I told you. And if you need tracing, or if you have some otherwise, I already said this, some large overhead in instrumentation or measurement, try to restrict it to the code regions that are of interest. Worst case, if you have a stupid tool that can only deal on a file basis, just extract it to its own file, to its own component, its own translation unit, and work with that, for example. But don't just go trace the entire program. First of all, it will take too long, and second of all, you will get much too much data that you then need to sieve through in order to get the actual content that you wanted to have. Yeah, still not done. I forgot about that slide, but that's an important one. Points of attack in order of benefit. This should be a general guideline how to debug your program and where to start. First, going from I/O over the network and the memory to the main computation. And this doesn't mean that your performance problems will always be in I/O. This is just sort of sorted according to the latency numbers in modern hardware. If you have a bug in your program and it's an I/O bug, it will take so much time, you shouldn't bother checking the network, the memory, or the computation. Generally speaking, there will be, of course, exceptions. So first of all, take a look at doing any I/O. If you're doing I/O, take a look at the file formats. Don't use text formats like XML. If a binary format and a checksum will also do. If it doesn't need to be human readable, you will simply reduce the memory, the storage requirements. You will reduce the bandwidth that you need. Think about buffering the data before writing it to disk. It's much faster than doing a lot of separate write operations. Consider using MPI I/O if you need more performance. Consider using RAM disks, for example, and maybe even change your data structures in order to not write out all the data, but only the data that you need to restore the data structure in memory that you need for computation. There's no reason why you need to write exactly what you have in memory just the same way to disk. If it's more efficient to change it first and write it to disk, then do that. Going over to the network, which is the next thing. Take a look at the communication patterns. Maybe they can be optimized. Take a look at non-blocking communication. If you spend a lot of time in waiting states, you might want to hide this latency with computation in between. Take a look at one-sided communication. If you have a lot of MPI calls, or if you have an unknown number of MPI calls for which you first need to tell the receiver how many people are going to talk to this process now. Take a look at the topology mappings, how to map your ranks to the actual hardware. Take a look at load balancing, because load balancing usually means you need to exchange data over the network. If you overdo this, then it will outperform the performance gain that you get by doing load balancing in the computation part. Once you're done with that, check memory. Check the data structures that you're using. If you don't need data to be sorted, then don't use a set. And if you do a lot of lookups and very few inserts, don't use a vector, but use a map, for example, right? Think about what you're doing in order to save time and which operations you really need. Think about the NUMA and affinity topics that we discussed, cache optimization, slack tiling, properly aligning and padding data, and so on. And once we're done with that, we're really so high in the bandwidth and so low in the latency that we need to go into the core and into the actual computation. And then you should check, do I use vectorization or am I not using vectorization, and should I enable it somehow? Should I change my data types? If I can do my computation with floats instead of doubles, I can get twice the number of elements in my vectorized registers. Might be a good thing to do. Check any intrinsics. If your compiler is not auto-vectorizing your code, try to use OpenMP. If you don't have OpenMP SIMD available, maybe resort to actually using GCC intrinsics. And again, of course, load balancing, and also consider hardware changes. If nothing else helps, switch to hardware that has either faster cores or slower cores, but more of them, and simply adapt the hardware to your actual problem. And using this top-down approach, which is sorted according to increase in bandwidth and decreased latency, or decreasing latency, this is usually how you should address slow programs from the first step to the last step, so to speak. And the idea is simply to not deal with memory or computation if you have slow I/O, because if I/O is done in a bad way, it will outperform any optimizations you do in computation, for example. Okay, finally, the summary. We talked about functional debugging. The idea is to adhere a lot to coding guidelines and best practices. This is a lot like quality engineering, I told you, but these topics are really important. As I told you, this is personal experience that I gained over the past few years. Especially relevant for parallelism because it's so complicated. Know your programming models, know your languages, the hidden semantics, and don't trust any of those automatic tools blindly. You can use them, but always do a sanity check on whether this actually makes sense, what the tool is telling you. And for performance debugging, don't underestimate the power of very simple tools like Top or HTOP, for example. There are many more advanced tools out there, but they're not straightforward to use, and they can take some time to set up and compile and use properly. And also, know your hardware and know your program hotspots. Don't try to debug something in your program that doesn't make up a majority of the runtime of your program. First check where are the bad portions, why are they bad, are they memory bound, are they computationally bound, and then start to optimize them. And with that, I conclude the lecture.